Welcome back. We're still going to push ahead through chapter 1 as we review limits again. So yesterday you were working with a lot of algebraic, graphical, substitutional, working on limits. Today our limits are going to focus on infinity and how that plays into the concept of a limit. We'll look at asymptotes, we'll revisit the squeeze theorem again, and then we'll introduce the concept of an end behavior and how that relates to infinity as well. All right, so as we talked about last year, infinity has two versions, two sides. There is a positive and a negative infinity, and so you should be comfortable with both. You should be comfortable with positive and negative infinity as it relates to x, so that would be going left and going right, but you should also be comfortable with positive and negative infinity in the y terms, so going up and going down. So not just to the right, not just to the left, but also to the up and down as well. When you're working with infinity, you can do all the same things that you could do with regular limits. You can add limits together. You can subtract limits from each other as long as what it's approaching is the same. You can multiply limits. You can pull k values, constant values, out to the front, and so then you have your k out in front. That's totally legal. And you are allowed to divide limits as long as the limit that's in the denominator is not equal to 0, of course, because you can't divide anything by 0. So the type of asymptote that infinity is connected to depends on where infinity is in the limit setup. All right, so if we have infinity is what we are approaching, okay, so as x approaches the left or as x approaches the right side. If that is equal to b, where b is a constant, what that means is that your graph is leveling off. Okay, your graph is approaching, and then what we call that is a horizontal asymptote. So that kind of version is going to produce a horizontal asymptote. And you can have different horizontal asymptotes on different sides of the graph. You can have one horizontal asymptote on the right side of the graph and one horizontal asymptote on the left. They can be different, but as long as it's approaching a constant, when you take the limit approaching infinity, positive or negative infinity, that's called a horizontal asymptote. If you have x approaching b, okay, so there's your constant again. So if you have x approaching a constant, and if that's equal to plus or minus infinity, okay, that's a different kind of asymptote. That means it's like you're hitting a wall, not hitting a ceiling, but hitting a wall. So think of it that way, okay? So you've got your horizontal asymptote is like a ceiling or a basement. It can't go any higher, it can't go any lower. Those are the boundaries. Okay, when you are having infinity as the result, now you're looking at a vertical asymptote. And those are boundaries on the sides. They're like hitting a wall and not being able to go past it. So you might have a wall on your left and a wall on your right, and you cannot get beyond that in terms of your graph. And these are extending as those boundaries. Now, if infinity shows up in both places, so if you have plus or minus infinity, and the limit is also equal to plus or minus infinity, we say that that is unbounded. There are no boundaries. Okay, and then there are no asymptotes. So the graph is just going to be going as far left as it wants, as far up as it wants, or as far right and as far down. There are no boundaries on that. So sometimes I feel like it helps to be able to see things visually. All right, so if B is the horizontal asymptote, so remember we're talking about this as a ceiling, okay? So then B is going to be this dotted line that's coming across here. Y equals B. And then your graph will be limited on the left and the right. So no matter what the graph is doing down here, when it comes up here, it will see that as a ceiling or a boundary, and it will never be able to cross that boundary. That is a horizontal asymptote. So the limit either as x approaches positive infinity or as x approaches negative infinity, it's reaching that same ceiling. That y equals b is the limiting factor. Here's a graph that has a horizontal asymptote that looks a little different, but the horizontal asymptote is coming right across here. And one side of the graph will never, both sides of the graph will never cross that line. Okay, there is your y equals 1 as a horizontal asymptote. So visually we can see it. And if you look at part A, if we're looking at x approaching infinity, so the right-hand side, we are approaching 1, but we're doing it from the positive side. So we say 1 plus. So it's like we're a little above 1. We're a little higher than 1. And if we're approaching x is negative infinity, then we have 1 minus. So we're a little under, or a little lower. You can confirm that on the table. These values are less than 1. They are slightly smaller than 1. These values are slightly greater than 1. So you can see it visually by looking at the graph. You can look at it as a table. You can do it that way, but you can also do it algebraically. Algebraically would be if you divided this into common denominators. So you had x over x, and then 1 over x. That's algebra, common denominators. And then reducing x over x here reduces to 1 plus 1 over x. And then if we took the limit of that, so the limit of that value, so then the limit as x approaches positive infinity of f of x would be the limit as x approaches positive infinity of 1 plus 1 over x, which is, now we're substitute 1 plus 1 over infinity. 1 divided by infinity is 0, a form of 0, but that's 0 plus. So we get 1 plus. So that's proving it algebraically. So you're on the upper side of 1. So you can do it by looking at a graph. You can do it by looking at a table. You can also prove it algebraically. All right, vertical asymptotes. Again, remember, vertical asymptotes are when we're going to hit this wall. So that would be x equals a, and we can approach it from the right or the left side. And so you could say, all right, on the left side, maybe the graph looked like this. The graph is happily coming along, and then it just about comes to hit that wall and shoop, it heads straight up to infinity. So then we say the limit as x approaches a from the left-hand side of f of x, that's heading up to positive infinity. Maybe on the other side, you might have the graph, and then it's going to come straight down. Like that. All right, and so then we would say, okay, as we come up on that wall, the limit as x approaches a from the right-hand side, well, this one is heading down to negative infinity. So those are vertical asymptotes, what they would look like. So here's a graph that has a couple vertical asymptotes. We've got one vertical asymptote coming down through here, and that value is x equals negative 2. And then we have another vertical asymptote, and that one is on the other side, symmetric, x equals positive 2. So visually, looking at that, we can pull some of the values off. So if we're looking at, okay, approaching the negative 2 one, but approaching it on the left-hand side, that'll be this part, and so we can see that that's heading down to negative infinity. But approaching negative 2 from the right-hand side, that's this branch of the graph, and so that's heading up to positive infinity. Positive 2 from the left-hand side, that's here, and that's also positive infinity. And then 2 from the right, that is heading down, so negative infinity. And so what if it didn't have right or left? What if it said x approaches 2? And it didn't have a plus and it didn't have a minus. Well, then we have to say it does not exist, because approaching 2 from the left is positive infinity, approaching 2 from the right is negative infinity. Those two things are not equal to each other, and the definition of a limit is that the two sides have to be equal. And so therefore we say it does not exist, because it's not possible for those two infinities to be equal to each other. Could you do this algebraically? For sure. You just need factoring in this one. So 8 over, and that would be 2 minus x, and then 2 plus x. And when you plug in your limits, plugging in -2 from the minus side or -2 from the plus side, you can work out different limits algebraically by using a version of plus or minus. All right, and end behavior is just another name. It's a synonym. It means the exact same thing as a limit approaching infinity. So if you are asked to find an end behavior model, it's asking what is it doing on the ends. So the two ends we're talking about, there's the right end of the graph, and that would be when x is approaching infinity. And there's the left end of the graph, and that would be when x is approaching negative infinity. So end behavior just means that you're finding the limit and figuring out if it has a value. Does the behavior have an end to it? Does it have a ceiling? Does it have a basement? Does it have something that's the lowest? And can you come up with some on the right side and some on the left side? So they don't have to be the same. One function can have both a left and it can have a right end behavior model. They don't have to be equal to each other. They can be doing different things on either side. End behavior models really are quite slick. They work really well when you are dealing with a polynomial. So a numerator that has a polynomial and a denominator. So maybe something like this. Find the end behavior model. So if you translate that, that just means find the limit. So we will be finding the limit of f of x. And we'd like to do that algebraically. And the best algebraic technique is division. But what do you divide by? Okay, you always divide by the highest power available to you. And the highest power in either of these polynomials is x squared. So we would be dividing every term by x squared. So 3x squared would get divided by x squared. 2x would get divided by x squared. 5 would get divided by x squared. And then in the denominator, 4x squared gets divided by x squared, and 7 gets divided by x squared. So remember, in algebra, everything is legal as long as you do it to all available pieces. So that's why we're doing it to all 5 parts. So we're left with 3 minus 2 over x plus 5 over x squared, and then the denominator is 4 plus 7 over x squared. Now we get to drop infinity into our model, so that would be 3 minus 2 over infinity plus 5 over infinity squared, and then 4 plus 7 over infinity squared. And when you're dividing by infinity, it's all a version of 0. So we have 3 minus 0 plus 0 all over 4 plus 0. Now you don't have to worry about whether the zeros are pluses or minuses, because we're not being asked if we're coming on the top half or top side of the value or the bottom side of the value. We simply are just asked for the end behavior model. So the end behavior model is 3/4. So what that means is that this function out at the end, at the right end, has a ceiling of 3/4. It will never go beyond 3/4 as its value. That is the end behavior model. And I did the right side because I was doing x approach infinity. If I was doing the left behavior model, I would do the exact same thing, just approaching negative infinity. And in this equation, I would get the same answer. Okay, that was just summarizing that. All right, so the last thing we want to hit up is going back to that sandwich theorem that we introduced the other day, and how sandwich theorem can help us support what we see, both graphically for an end behavior. So the end behavior is not a polynomial. If that dividing by the highest power doesn't work, then we need something else, which is what we think the sandwich theorem is going to be. So if we're looking at this graph graphically, it appears to oscillate. Okay, it dips below the x-axis and then above the x-axis and then below the x-axis and then above the x-axis. And the table would support that. The table would support that it's going from a negative to a positive, and then a couple negatives, negative, 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 and then back to a couple positives. And these values just keep switching, negative, positive, negative, positive. So it's oscillating. We can hypothesize that y equals 0 is the horizontal asymptote for this function, the end behavior model, but can we prove it? So we're going to prove it using the sandwich theorem. And what we're going to do is actually a really, really awesome algebraic trick of substitution. So they're going to give us a hint about what they want us to substitute by saying, try this instead. Instead of f of x, try f of 1 over x. And so that substitution means you'll be replacing 1 over x with the value of a. So this is a direct substitution. If 1 over x is equal to a, and it really will be better, I think, if I can show you this, okay, which is a over 1, and we cross multiply. Turns out that x is equal to 1 over a. So if 1 over x is equal to a, then x is equal to 1 over a. Now I want you to go back to this limit and replace everything. So everywhere we see an x, we're going to put 1 over a. So this would be the cosine of 1 over a instead of x. And then denominator instead of x would be 1 over a. And then the limit has to get replaced as well. So if x approaches infinity and x is the same as 1 over a, so in other words, if x is getting really, 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 really big, then a is getting really, 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 really small. All right, so see how I did that? Okay, so what does that look like algebraically? So now we have the limit as as a approaches 0 of the cosine of 1 over a, and then divided by a fraction, which is the same thing as multiplying by the reciprocal. So that's multiplied by a instead of divided. And then we can substitute in. And this a approaching 0 is going to go right here. And it's going to go right here. And when I substitute a approaches 0 in for a product, then the value is 0. So the limit has to be 0. I just proved it by doing a substitution. That algebraic substitution is such a slick way of doing a proof. Okay, I know we think of proofs as being geometric, like something we did back in geometry, a proof, but this is what we're doing. We're doing a proof by algebra. So let's use that same technique to find the proof of this limit as well. So we are hypothesizing, maybe we've looked at a table or we've looked at a graph and we hypothesize that the limit is 0, but can we prove that the limit is 0 using this same algebraic technique? Okay, so the substitution is going to have to do it with 1 over x again. And so we're going to say I'm going to replace 1 over x with a. So if I'm going to replace 1 over x with a, it's going to do a lot of other replacing as well. Sometimes it's helpful to think about what the cross multiplication would be on that. So if I say, okay, yeah, a is over 1, and then I cross multiply, then x is equal to 1 over a. All right, so let's go back to our limit. And what will our limit look like? What goes in for x squared? Well, x itself is equal to 1 over a, so x squared must be equal to 1 over a squared. So I'm going to have 1 over a squared times the sine of, and then 1 over x is a, and that's our limit. And then what about the approaching part? Instead of x approaching 0, a has to, do the opposite, because they're reciprocals of each other. So if x is approaching 0, then a has to approach infinity. So now we're going to use the property that we can split up 1 over a squared into 1 over a, and 1 over a, and sine over a. And then we can split up with the product. We can say I want 1 over a to be separate from the limit of 1 over a times sine of a. The reason I separated that is because I'm thinking that this is something we worked with yesterday. So now I've got 1 over a times the limit, and then I can put them together as sine of a over a. And this is a limit you should have memorized. The limit as x approaches infinity. We proved it yesterday with the sandwich theorem, and we proved that this value itself is equal to 0. So then that would give me the limit as x approaches infinity of 1 over a. Oh my goodness. I just realized all this time I've been writing x approaching infinity instead of a approaching infinity. I'm so sorry. Let's go back and fix that. You probably were caught on to that faster than I did. So let me fix that all. Okay, times 0. So 0 times that limit, regardless of what that is going to turn out to be 0. And so we've just proved algebraically using that substitution technique, again, that the limit equals 0. All right, so anytime you're trying to find an end behavior model, it's simply the same thing as finding the limit as x approaches infinity. And you can use various techniques. Your techniques are divide by the highest power. So let's quick review those. If it's a polynomial, check. That'll be divide by the highest power. If it's not a polynomial, okay, so that works for polynomials. If it's not a polynomial, then your other is going to be an algebraic substitution. And you're going to try to switch out a for 1 over x or 1 over a for x. Use a reciprocal substitution, some kind of reciprocal property, and then that will alter your limit and allow you to work algebraically with that. So those are when you're finding an end behavior model, which means finding a limit approaching infinity, those are two of the things you're going to rely on, two of the strategies.